Hello everyone, I hope you are doing good. In today's video, we'll discuss about the resonance effect. So resonance effect has been described by many books and we are understanding this effect for a long time. But when I was thinking about to start this video, I was thinking to cover few of the definitions which are recommended by the IUPAC. It happens that many of the time we are coming across the different materials that we are getting the materials from the different excellent reference books, but a few of the times the concepts or exact definition, if it is being asked in interviews, uh, that what is the exact definition of this, and that time the conceptual definition of the particular concept has to be in our reference, or it has to be with us. So for that reason, these two definitions I have taken from the IUPAC recommendations. And one of the thing, I'm going to make a separate video on this, how to use the IUPAC website, and this is really helpful material for the students as such. So let us start with the today's topic, resonance. By the IUPAC recommendation, as I said, resonance is the term which gives the representation of electronic structure of molecules which are contributing the structures. And this is the concept which is given by the conceptual understanding by the quantum mechanics, especially the valence bond theory. As we are knowing about how the bonding is playing a role in any molecule. So the valence bond theory is explaining the concept how the bonds they are getting formed, and through this representation of electronic structures that are helping to write the resonating forms. Another thing that one needs to understand with respect to the resonating or resonance effect, or with respect to the understanding the importance of resonance effect in a organic molecule, and that is related to the resonance energy. We are observing those molecules which are showing a resonance effect. They are with the extraordinary stability, and reason is also there. We are going to discuss this reason also in this video. One important thing that we need to understand with the concept like a delocalization, what is a delocalization and what is the exact meaning of this also we are going to study in this video. Many of the times, resonance is also accompanied with the synonym that is the mesomerism. It is also a similar concept. It is having a different significance and the place in the dictionary of IUPAC. So that's the reason why I put it in another platform. Here you can see the resonance is having a synonym with the mesomerism. It is a particularly associated with the Lewis formula. I think many of the times when I ask this question to students, can you write the Lewis structure for any molecule? Students are not getting the point. So those who are writing the reaction mechanism, they has to be associated with the exact understanding of the dot structure or the Lewis structure. And these are the concepts. They are very well explained and documented by the IUPAC. All those definitions that we are seeing from the books, that is related to this. What is the resonance effect? Resonance effect is the effect that is transmitted through particular molecules which are having the conjugation. And this effect, as we are having the conjugation, this will be throughoutly distributed to that part. And if we are thinking about the conjugation, we need to think about the planarity. Planarity is the concept that I will explain in the same video why it is associated with the importance. Which molecules they are showing a resonance, that also we need to understand, we need to take into account. First thing, the lone pair and the double bond, if it is in the conjugation, it will show a resonance. Second thing, two double bonds, if they are in a conjugation, it will show resonance. Let's take two examples over here. As you are seeing the benzene structure you are observing here, and as we'll go one by one, as you are seeing, this is associated with the part that we talked about. This is this system in the benzene here you are observing. There's all these orbitals, they are parallel to each other, and all these orbitals, they are exactly in the same plane. Okay, so we are seeing that these orbitals, they are parallel to each other, and the concept with respect to the planarity is exactly fulfilled in the case of benzene, so that the delocalization electron is possible. So suppose we are talking about derivatization of benzene, and you are taking the example of a phenol over here, then benzene skeleton is the same, only the thing is the extension of connectivity with using a OH. What is the case we are observing over here? The all p orbitals of the carbon you are observing over here, they are having a parallel orientation with the one of the lone pairs of oxygen. So suppose I want to resonate, I want to conjugate the lone pair of oxygen through the system, I can do like this. And in this way, I can delocalize the electron so that the lone pair of oxygen and these p orbitals of this benzene skeleton, they are exactly in a same plane, so that I can resonate this to write their resonating structure. So this concept has to be fulfilled, that the system has to be conjugated and it should be associated with maintaining a planarity. I hope so you can understand this concept with respect to the structures of a benzene and phenol. One needs to understand these five concepts so much clearly before going towards the applications of resonance. First thing that we have discussed, that is a conjugated system that we are in need of. Second thing, it is related to the planarity that we discussed. The all the orbitals which are becoming a part of the pi system, they has to be in the plane so that it can easily delocalize the electrons. Third thing, and it is a very important, many of the time it is a becoming a crucial part to explain the different reactions on the basis of polarization. So what is the idea that we are getting the polarization from the resonance effect? Let's see the example over here. This is the phenol, and this is delocalizing the lone pair of oxygen over here, and it is forming a negative charge. So you are getting the positive charge on oxygen and negative charge on the carbon. So directly it is forming the two poles, that is a positive and negative. So resonance effect, as it is, we are saying this is a polarization in a pi system, and this is leading to form of poles. And this system is throughoutly operating through the pi bonding that we need to understand. What is the meaning of the resonating structure? As you are seeing over here, the phenol, when we are writing the resonating structures, we are getting the first, second, and third structure. What is the meaning of this? The meaning of this all representation is the negative charge which is forming on the carbon, it gets distributed over other carbons, and all these possibilities we are writing, and these probabilities or these possibilities, they are underlined as a resonating, they are underlined as a resonating structure. So all the possibilities that we can draw with respect to the stabilization of the charges that are being formed in the system, they are called a resonating structure. Another important part, and I must tell you one thing, I am making a separate video to represent the exact meaning of the arrows. And I must tell you one thing, many students I have seen, they are not able to write the proper arrows in the reaction mechanism. So that's the reason I keep it with the different color, so that the student can keep it this thing in mind quite well. Resonance arrow is shown by the double headed arrow, as you are observing here, and this is the meaning of the concept that the electrons are delocalized. All these systems that you will see, the total count of the electrons in all over the resonating structure will be the same. Only the thing is we are just changing the position of electrons through the resonance. So this is overall effect that we are observing in a system which is associated with the conjugation, planarity, that is forming a polarization, different resonating structures we are writing, and they are shown by the resonance arrows. The concept that we need to understand, what is the localized and the delocalized electrons. Suppose we are considering the diversification in molecules. Let's say we are having the set of molecules that this is a alkane, and the second example I have taken, this is for the this is as a alcohol. So what is the meaning of localized electrons? Localized means, you can see this is mentioned as they are showing not at all movement. What is the meaning of this? In the case of alkane, as we are observing, there are two types of bond. There's the CH and the CC bond. So whatever the electrons which are present in a CH bond, or whatever the electrons present in the CC bond, they are not at all showing any movement. So we can say the position of these electrons between the CH or between the CC, it is 100%. So we are not at all expecting that the position of these electrons will move either from this bond. If you're talking about the CH bond, the pair will be here completely. CC bond, the pair will be completely, you will find in between the carbons. Similar case in the case of alcohol, you are seeing the lone pair, even though it is lone pair is considered to be more labile, more we can say it's a reactive, but you'll see in the case of this alcohol, the presence of lone pair on oxygen, it will be 100%. We do not expect that this will have any movement other than the oxygen atom. So therefore we can say these electrons are localized. They are having a 100% probability that you will find these electrons between either the two nuclei or on a particular atom. On exactly opposite to this, we are having a concept that is called a delocalized electrons. Let us take an example of benzene, and for the sake of simplicity I will give the numbering 1 2 3 4 5 6. So those electrons which are present in between 1 2 and 3 4, we cannot say they are exactly locating between the two carbons. So we can do like this: we can show resonance, and the electrons which are present in between a 1 2, it will move between a 2 and 3. So in this way, we can also show resonating structure for the phenol as such. The lone pair on oxygen, it can move from oxygen to carbon. Similarly, in the case, suppose we are extending, we are lengthening the process of resonance, then we are connecting the para nitro group so that the lone pair on oxygen, it get conjugated, and lone pair on the OH group can be extended or can be delocalized through the resonance, so that the lone pair can reach to the oxygen of a nitro group, so that we can say the movement of electrons is available. Electrons are moving from one atom to another atom. If this is the possibility, and if this is passing through the pi system, this concept is called to be a delocalization of electron, and this is the fundamental or the crucial part in the resonance. One important thing that we need to understand, what is the conjugation. We are having the three examples. In the first two examples, it is said, and the definition is saying that the what is the conjugation. Conjugation is nothing but it is having a presence of single and multiple double bonds like this. So suppose you are seeing the first example, the double bond separated by the second double bond by a single bond. This is the same concept over here. So alternating single and multiple bonds, this is the identity of conjugation. Here also you are seeing this is a double bond, this is a triple bond, and this is separated by a single bond. But in the third example, you are observing this is the double bond, this is the double bond, and there are two single bonds in between. So this is not a conjugated system, that we need to understand. So suppose question is asked like this: identify which of the molecules in the following they are showing a conjugation. I hope you are able to identify the correct molecules. So we are getting the exact idea about how the resonance effect is working, and we need to understand few of the fundamental rules to write the resonating structures, and these are very simple. This is again with respect to the things that we have seen with the Lewis structures. The Lewis structure, as this is giving idea about which center is stable, and the stability is, of course, it is based on a completion of octet or having a positive and negative charges on the respective centers. It means if we are having a negative charge on an electronegative atom, it has to be stable. If it is an electropositive atom with a positive charge, it will be stable like this. This is the natural process, and these are the rules that gives us the idea about the stability of different structures. One more thing that we need to understand, how many charge species we are forming in the structure, that also playing a role. So minimum the charges are formed in the system, that will be favored. One thing that we need to understand, and that is becoming crucial to give a justification for various reaction, and that is related to the number of resonating structures. The system, the thing, if you are remembering in the initial two slides, it is related to the resonance energy. What is the meaning of this? As we are seeing in this system, wherever we are writing the resonating structures, we are getting the positive or the negative charges, the polarization. If the charges which are being formed in the system, if they are stabilized by more resonating structures, that means, let us take an example over here in a in aniline, the negative charge which is formed over the ring, it is distributed over a carbon. So if we are having the more carbons, so that the negative charge is distributed over the more centers, so that will contribute the stability, extraordinary stability, and that is nothing but a resonance energy. Broadly, resonance effect is classified into two classes. First one is a positive and second one is a negative. This is a very simple concept. Let's take an example of aniline. Aniline is having a nitrogen with the lone pair, and this nitrogen lone pair we can show resonance, so that nitrogen will have a positive charge and the negative charge is distributed over a phenyl ring. And of course, the negative charge it delocalizes over the other carbons, and this system shows resonating structures. Resonating structures, that is, we have seen like the first, second, and the third one. We are observing overwriting the positive resonance effect, that this is forming the charges. This is forming a carbon ion over a cysteine. This is forming a carbon ion over a cysteine because your group which is showing the plus R effect, which is donating electron to the cysteine, so that it is forming a negative ion. So this cysteine, particularly this cysteine, is becoming a electron rich. So those groups which are showing a plus R effect, they are able to enrich the cysteine so that it will be available for the nucleophilic reactions. On the contrary, we are having the negative resonance effect. You will find this is the group that is showing a negative R effect. So it withdraws electrons from the cysteine. As you are seeing here, nitro group, which is a strong electron withdrawing group, so that it pulls electron from the system and it is creating a positive charge in a system. Here the system is the phenyl group over here, and over a phenyl group you are finding the formation of a carbocation. So this system is forming the charges, and formation of the charges, that is a carbocation. And these carbocations, once they are forming on a ring, so we are generating the electrophilic centers on this. So this system is susceptible, or it is more prone for the electrophilic capacity, so the nucleophiles can attack over such system. So this is the basic idea about classifying the resonance effect. We'll just highlight few of the things related to the classifying the abilities of different groups to behave either electron withdrawing or electron donating. As we have just discussed, the nitro group, as you are seeing, this is able to withdraw electrons. Similarly, sulfates, they can also do the same. Carbonyl groups, that you are seeing, whether it's a aldehyde, it's a ketone, carboxylic acid, ester, or amide, all are having a capacity so that it can pull the electrons, and that can generate a positive charge over a system. So therefore, all these groups, they are example of minus R effect. They are strong electron withdrawals to the resonance. On the contrary, on the right hand side, you are seeing those groups which are showing a plus R. All these groups are associated with the lone pair. They are the heteroatoms. So they are easily giving electrons in the system, and they are generating the system electron rich. So this is the thing that we are understanding. These are the groups or atoms. They are able to donate electrons to the system and making the system more electron rich. We'll see some of the examples, and through this we'll try to recollect the things that we have discussed earlier. Question is asked like this: why the phenol is acidic than the cyclohexanol? Actually, when such questions are asked, they are based on the acid and base concept. And these concepts can be explained with the help of resonance effect. As we have seen that such as some of the cases can be explained on the inductive also, but this example can be explained with the resonance effect. Phenol, as it is behaving acid, by donating H plus, it will form a conjugate base. This conjugate base, as you are seeing the oxygen, as it is in a conjugation with the phenyl group, so that the negative charge, whatever it is formed on oxygen, can be distributed throughout the system with the resonance effect. So negative charge which is present on oxygen, it will come on one or carbon, second carbon, and third carbon. So we are able to write the resonating structures, that is showing the stability of the conjugate base of the phenol. On the contrary, if you are seeing the cyclohexanol, why it is a weak acid? Because once it is donating H plus, it is forming a conjugate base, but this base is not at all having any stability, no resonance stabilization. you are seeing this is not at all associated with the resonance stabilizer. So we can say the no resonance stabilization. So in this way, we can simply explain this concept that one phenol molecule which is forming a conjugate base, and this conjugate base stabilize with the resonating structure, and which is absent. This concept is absent in the case of cyclohexanol. Its a conjugate base is not stable because of lack of resonance. So therefore, phenol is a we can say it is acidic than the cyclohexanol. Similar example, carboxylic acids, why they are stronger acids compared to the alcohols. As you are seeing, as it is donating H plus, it is forming the oxygen with the negative charge, and the negative charge on oxygen can be stabilized with the resonance. So we can say this is a resonance stabilized conjugate base, makes it a quite stable. The conjugate base is a becoming a stable because of resonance effect. If you are thinking the similar case with the alcohol, by donating H plus, you are seeing it is a forming a O minus, but this O minus is not at all having any possibility that it will show resonance, because this O minus, you are observing that this is separated by two single bonds that we have seen. So this system is not conjugated. So therefore, this will not have any stability, because the negative charge on oxygen, you will find it will be 100%, and more the negative charge, of course, it will be a more reactive, so that alcohol is not at that much acidic as compared to the carboxylic acid. So this concept can be explained on the basis of resonance effect. On the contrary of this, few of the questions can be asked with respect to the basic nature of the few of the molecules. Let's take the example of guanidine. Guanidine is a very interesting molecule where you are finding the three nitrogen atoms. And three nitrogen atoms you are observing. If either of the nitrogen you are showing that is getting protonated, you will get the conjugate. This is the conjugate acid of guanidine. And you are observing that the conjugate acid of the guanidine can be easily stabilized with the resonance. So for example, this if this nitrogen is getting protonated, positive charge on the nitrogen can be easily stabilized by the resonance effect of this nitrogen. Once this nitrogen is becoming a positive, this nitrogen is coming into the picture, and it will donate the pair of electrons, and it will stabilize this. So overall positive charge which is formed on a nitrogen can be easily shared by other two nitrogen atoms. So therefore, the system is becoming a stable because of resonance. So simply we can explain the conjugate acid of guanidine can be easily stabilized through the resonance effect of other two nitrogens. So therefore, it is a resonance stabilized conjugate acid of guanidine, makes it a strong base. This is the last example, and it is quite interesting. Many competitive examinations they have covered this example: aniline, cyclohexylamine, and the diphenylamine. These are the three molecules you are finding over here: cyclohexylamine, aniline, and the diphenylamine. Question is, aniline is a less basic than cyclohexylamine. So you are seeing the aniline, which is less basic. So this is a we can see the cyclohexylamine is a stronger base than the aniline. Why it is a stronger base? In the case of cyclohexylamine, you see this is a lone pair which is available on a nitrogen. This is a completely available. Why it is a completely available? Because lack of resonance. You are seeing there is a no resonance. So therefore, this lone pair is 100% available. So it can easily behave as a base. But in the case of aniline, as you are observing, the lone pair which is available on a nitrogen, it is in a resonance. It is showing a resonance, so that the lone pair on a nitrogen, it gets distributed over this carbon, this carbon, this carbon over here, and therefore availability of electrons, as we have seen, the base is nothing but it is the species which is easily donates pair of electrons. So here you are observing the availability of electrons on nitrogen is reduced, and that is because of resonance effect. So therefore, it is a less basic compared to cyclohexylamine. But suppose you are comparing the aniline with the diphenylamine, you will see, for example, if I am just giving for sake of understanding the notations for the two rings as A and B, you are seeing the lone pair of on a nitrogen can be delocalized over either a B ring in this direction or A ring in this direction. So the lone pair on a nitrogen is distributed over the carbons, and it is having a more resonating structure. So the more electrons will be delocalized over the carbon. So the less availability, or we in this case we can say this is available, or we can say this is with the least availability among these three molecules. So therefore, this concept can be explained. Aniline is a less basic than cyclohexylamine, but it is more basic than the diphenylamine. So in this way, we can take the help of resonating effects to explain the acidities and basicities of few of the organic compounds. And resonance effect is definitely having importance for the structural characterization of few of the molecules in the context of their reactions. This is also a very interesting example I found, and this example is covering the two important rules of resonating effects. Thalamide and the phenol, it is considered to be the almost equal acidities. As this is the word that is introduced, but suppose someone wants to get into the exact meaning of this is interesting. Why it is interesting? One rule that we have seen, if we are having the more number of resonating structure, number of resonating structures, that is also important, that we are taking or we are giving importance to this number of resonating structure. And the second rule is negative and positive charges on electronegative or electropositive atoms, that is of our importance. So what we are observing over here in the case of thalamide, if it is behaving as an acid, it will give H plus and it will form a conjugate base. This conjugate base that you are observing, the negative charge can be distributed over either this oxygen or this oxygen. So we are having the two resonating effects. And it is good that the negative charge is residing either on the nitrogen or oxygen. In the case of phenol, it is forming the conjugate base, that is a phenoxide, and this negative charge on oxygen can be distributed over carbon through the resonance. In this case, we are getting the three resonating structures, and as the thing that is suggested by the one of the good things about the resonating, that is this is associated with the more resonating structures. Here we are having the three resonating structure, here we are having the two resonating structures. So the student may get confused. For example, in the phenol, it is associated with the three resonating structure, while in the case of thalamide, it is having the two resonating structure. Then which will be the stable? At this moment, the another part also we need to take into account. In the case of thalamide, even though it is associated with the two resonating structures, negative charge is it is residing on either nitrogen or oxygen. So therefore, it is we can say the compensating effect. Even though it is associated with the two resonating structures, it is comparable with the three structures that are formed in the case of conjugate base of phenol. So, my dear students, it is always we can say application part is becoming interesting if you are dealing with some newer molecules. I hope you are finding this is interesting, and if you are really feel that this material is helping you and this is going out to give a direction about how to study the fundamental concepts or general organic chemistry with some interest, I request you subscribe the channel, share with your friends, and put your comments, because your feedbacks, they are useful. I mean to say, those students who are understanding better, if they are sharing their views, it will be helpful for me to make them content more useful for the students as well. This will be becoming a more interesting in the next videos. So thank you so much. Take care.